Life finds a way. A quote from the original Jurassic Park said by Dr. Ian Malcolm, or for you movie watchers, Jeff Goldblum's character. In the context of the film, it's said as a warning to the scientists and researchers that specifically designed the dinosaurs of Jurassic Park to be only female, believing that they won't be able to reproduce and therefore humans will be able to control them. Spoiler alert, they were wrong. The quote and its sentiment have become the main theme of the entire franchise. Can humans control nature? From a biological and evolutionary perspective, I find the quote quite inspiring. Despite unbelievable circumstances in the universe, life finds a way. To the fiery mouths of volcanoes, to the coldest depths of the oceans, life finds a way. In 50 years before this phrase would appear in any beloved dinosaur franchise, mathematicians and computer scientists would take an interest in the phenomena of life, developing a concept of computer science known as cellular automata, or robots that act like cells to play out simulations, represented by pixels or cells on a grid. It wouldn't be until 1970 when John Horton Conway would create the most famous cellular automaton in history, the Game of Life. Conway's Game of Life has a very specific set of rules that are an analogy to life itself. White pixels are alive and black pixels are dead. If a living cell has 2 or 3 neighbors that are alive in the current generation, it will live into the next generation. If the same living cell has less than 2 or more than 3 living neighbors in the current generation, it will be dead in the next generation due to underpopulation or overpopulation. And if a dead pixel has exactly 3 living neighbors in the current generation, it will be born again in the next generation. From these pretty simple rules, the simulations that can play out actually seem pretty lifelike, with patterns that actually stabilize and find a way to survive. There are dozens of these patterns to do a few different things, like just exist indefinitely without moving, cycle through different states, and even move. My favorite pattern is called the toad, which does this sort of breathing-like movement. And a lot of patterns have names, actually, like the glider, which glides across the screen, or the glider gun, which can actually generate gliders. Simulations can last a surprisingly long amount of time before reaching a stable point, and it's pretty mesmerizing to watch. If you haven't seen my last video, I like developing programs for the Game Boy Advance, so let's put Conway's Game of Life on the Game Boy Advance. The first question to starting any GBA project: which display mode am I going to use? Bitmap mode seems pretty obvious for this one since I want each pixel to function independently, but which of the 3 bitmap modes is the right one? Well, Mode 4 and Mode 5 have page flipping, which allows for the GBA to store screen data in 2 places, and then alternate between them, kind of like a display buffer, and it actually fits really well for this use case. I can store the current generation on the first page, and then build out the next generation on the second page. Then when the second page is complete, I can just flip the pages and then do the same thing again, but vice versa. Now, between Mode 4 and 5, the main differences are the display size and the bits per pixel. I will go with Mode 4 because it has a 240 pixel by 160 pixel display, which is just more pixels for more complex simulations. Now that all that decision making is done, I just need to code it up. The main loop will decide which page is the current generation and which is the next generation, and then iterate through every cell of the current generation, counting the living neighbors, and then applying the rule set to determine the state of the same cell in the next generation. After iterating through all the cells and building out the entire next generation, I will flip the page, and then the new generation is being displayed. The trickiest part of writing this code is that due to hardware limitations, you can't write 1 byte at a time, which means you have to write 2 pixels at a time. With some clever bit manipulation, you can draw individual pixels, so not a huge issue, but it could look messy if you weren't aware of this quirk of the GBA. And yikes, does this run slow. Holy cannoli. With a 1 pixel border, it's running calculations on 238 pixels by 158 pixels, which comes out to about 37,000 pixels per generation. The GBA just is not powerful enough to handle that many calculations. So we're going to need to make some serious changes to see any improvement on performance. If too many calculations are the issue, I can reduce the number of calculations by using less cells. Instead of each pixel being a cell, I can use a 2x2 pixel cell. This also helps see some of the patterns more clearly when running on hardware. In theory, it will run calculations on 1/4 of the cells, so 4 times faster. And with this change, I don't have to draw each pixel individually anymore, so we can avoid that whole bit manipulation thing altogether. You can draw pixels in pairs of 2, which will save a few computations per cell. Another optimization is to be careful about what types of pointers I'm using. The current generation will not be updated while we create the next generation, so I can access the current generation with a constant pointer, which also should increase performance a bit. And I haven't measured, but it seems like it might actually run 4 times faster. In addition to the random initial state, I also added a few different initial states to see some of the moving patterns in action, like the toad and the glider gun. I could have done this in a fancy way where I create a 2D array to draw out some initial conditions and then have my code read it, but instead I just hard-coded some of these patterns. That would be a neat expansion of this going forward, but since this is more of a proof of concept and a kind of a demo, I wasn't too concerned. And there we have it. Like Dr. Frankenstein, I have given life to this inanimate object. I'm pretty happy with it overall. It still doesn't run as fast as a computer could run it, but the GBA was never going to be able to keep up with a modern computer. I've uploaded the code for my naive solution and my more optimized solution in a GitHub repository linked below. And at its root, the game of life is a cellular automaton that has the same base functionality as most other cellular automata. Generate the initial state, and then iterate through all of the cells of this generation, applying the rule set to create the next generation. With just a few changes to the rules in the initial states, you can start designing your own cellular automata. I've already started working on a few of my own. Subscribe and click the bell icon to be the first to see them when I upload next. Thanks for watching.